Okay, so thanks first of all for the invitation and the opportunity to be at this great place. So I'm speaking about theoretical results we got on a method that actually David introduced. I mean, it's sort of probably based on older ideas, but he very much pushed that method. And there were a couple of theoretical questions left open and also sort of questions of universal practical implications. And I'm going to say a few things about that. So I'm going to introduce, first of all, optimal potential vorticity balance, more or less along the lines of previous work by David and Viodes. Then I'm going to give a little bit of theoretical background about slow manifolds. I'm going to talk about optimal balance and primitive variables, so basically the traditional velocity, height, density, whatever variables. And then the key point in my talk is about the use of nudging to actually numerically find a solution to the optimal balance problem. Okay, so I'm, I guess, preaching to the converted here. So most people will have seen balance large-scale flows where essentially pressure gradient forces balance the Coriolis force, and then we have sort of orthogonal to that in a certain nonlinear sense, internal or surface gravity waves. And the picture that I think was on David's slides as well is so the last scale flow is very much dominated by the potential vorticity. So here for Euler-Boussinesq, but you can write similar expressions for most geophysical flow problems. And then the slow equation, so to speak, is just the advection of potential vorticity. And we have sort of from an old paper by O'Sullivan and Dunkerton, sort of this picture of reconstructed flow from potential vorticity. And then to fully close the model, we have some sort of ageostrophic variable. So this could be divergence and ageostrophic vorticity, for example. Different choices are possible, of course. And then the fast equation can be essentially written as essentially a linear wave propagation part with a skew operator L that has sort of a large parameter in front, and then there are some nonlinear interactions to complete the model, and usually this n is complicated. Right, and then sort of that's basically the missing component here, and typically in geophysical flows much smaller. So this is what we are talking about here, and in order to understand what optimal potential vorticity balance is doing, we should look at, first of all, the Lagrangian formulation of the flow to just fix concepts here. Yeah, so everybody knows this Lagrangian velocity. So phi is the flow map, and then we have the definition of the flow. So essentially what phi is doing, it's mapping some initial fluid volume onto the fluid volume at a later time. And basically, advection of potential vorticity just means push forward by the flow map. And yeah, so the closure basically is done by PV inversion and needs to be augmented by some fast equation, like on the last slide for the ageostrophic quantities. All right, so what Viodes and Ritschl did is introduce a potential vorticity ramp in essentially this push forward of potential vorticity. So it's essentially decomposed just for technical reason into background potential vorticity that generates a steady state flow. And then sort of the anomaly of potential vorticity is augmented with a ramp function. Okay, and then we have the other equations, and they solved this as a boundary value problem in time with two boundary conditions. So at, let's say, a final time that I always call capital T for the remainder of this talk, they were imposing some potential vorticity profile Q star. This is given, and that is sort of my target potential vorticity distribution. And then at an initial time, t equals 0, they impose that there is no ageostrophic motion. So basically, the two ageostrophic variables in this case would be equal to 0. Okay, and then this is solved by a nudging iteration. Maybe I'll get to the full picture and then I'll point to it. So let's say, again, initial time here, that's more or less this boundary condition. So essentially projecting out fast motion, forward integration, you have then some general fields in all three variables. And at the other end, we have a target potential vorticity. So in general, this potential vorticity is not going to have much to do with the target. So it's being set to the target. Then we integrate backwards in time to the initial time. And this will have gravity waves. And so they are projected out again. And we have this, what I call a nudging cycle. So the nudging steps are basically this projecting out of fast motion. And on the time equals capital T and the restoration of the target potential vorticity field. Yeah. Full equations, but with the ramp function, of course. So it's not the original dynamic, but it's sort of. It's whatever it's going to be, right? And right. So well, it influences the potential vorticity inversion, right? So vorticity is transported to some place in time, and then in order to get the velocity field, you need to do the PV inversion, and the PV inversion, of course, then sees the ramp function. Then it doesn't have this term.
Actual value given by that from 0 up to the positions of the quantities are not of T. It's in the wrong position at that duration. So you restore right positions. Wherever they're going to. With perfect conservation, that would be the only idea was that we graph it up on each contour, or was basically
yeah. Yeah.
Model. Oh, well, it was purely guesswork. I mean, we'll be close. Notice that Q after that forward integration is set to the exact
Right. Yeah. Yeah, and I guess David's paper says it converges quickly, and we'll show it doesn't converge.
Not exactly.
Okay. Yeah. So. yeah, so that's basically sort of the idea. If converged, then we basically define the associated sort of slaved variables to the potential vorticity as whatever delta and gamma are at that point in the process. All right, so about the ramp function, so this is from the original Virdis paper. So it's basically a cosine function scaled appropriately. So at time t equals 0, the ramp is 0. At time capital t equals capital T, or here scaled to 1, it's 1. And it's very smoothly and with yeah, minor gradients. Okay, so question, why does it work? We started discussing that. And some other question, can this work in primitive variables only? And I'll show you it does. And then, of course, you can see this whole process is a boundary value problem in time. So one boundary condition is given at t equals capital T. The other boundary condition is given at t equals 0. And it's not actually clear whether a solution to that problem even exists as a boundary value problem in time. And then convergence. Okay, so what is the general underlying idea why it should work? So first of all, sort of the concept of a slow manifold. We think that in the slow manifold, the adiabatic variables would be given in terms of the potential vorticity by some slaving function. So this would define a manifold in phase space. And then the idea is that the slow manifolds are adiabatically invariant under slow deformation. That means if we change the equations a little bit slowly in time, then whatever is propagating on the slow manifold or approximately close to the slow manifold under the slow deformation actually keeps being on the deformed slow manifold. So the idea really that is already in Differential Virdis is, well, if we have this adiabatic invariance, then we do a deformation of the problem that ends up at one end of this deformation in some trivial case that we can handle. And in David's case, it was essentially where all vorticity is just the background vorticity, and we are in a steady state, and then we know what is fast and what is slow, because everything that is moving is fast, and we can just project it out. So I guess, I should mention some history. So I guess the idea of adiabatic invariance is very old, and since we are at the Schrödinger Institute, maybe it goes back to Schrödinger, I don't know, but the quantum mechanics people certainly were interested in basically the persistence of eigenstates, of quantum operators under slow deformation of things. And in the more mathematical literature, I just picked out Benetton and Fassot. I'm not sure if they were even the earliest ones. I think there's also some work in the 70s already in the mathematical literature on adiabatic invariance. Okay, so Virdis and Rich. Yeah, I mean, I probably forgot an infinite number of publications and these few. And essentially, Colin Cotter, I should mention, because he was the first who realized that basically the Virdis and Richter method had some connection to this big existing theory of adiabatic invariance. And we rediscovered it somehow and then found the Cotter paper and were sort of disappointed. But anyway, so I would like to give one toy example that somehow explains a little bit about how the method works and the limitations or additional condition also. And this is sort of one toy example that comes from the mathematical sort of slow manifolds theory. So it's essentially two coupled oscillators with a coupling function. So one oscillator is written in action angle variables. It's just a harmonic oscillator. So the action is constant and not listed here. And basically the angle is going around the unit circle here. Right? So pretty trivial. And the second harmonic oscillator is just written in complex variables because it's basically easier than having a 2x2 system. And then there's sort of this coupling function f, and I've already written the ramp here. Okay, and what is done in sort of simple example of slow manifold, so there's no ramp function in that case, so we just have the coupling function, so we write it in a Fourier series, and an exact slow manifold would be given by the following expression. So we seek a variable p from this sort of second operator that fields the oscillator, that fields the first oscillator. So we want to write p as some function of the theta variable. And if you basically Fourier expand everything and basically equate coefficients, then we find this expression here. And this is exact, but you will also notice there's the possibility for resonances because there's a possibility for zero denominators here. Right? But this is sort of explicitly computable, or as explicit as it gets in that business. And then, of course, the explicit computation can be also done with optimal balance. So now we have the ramp function here, and we have the boundary conditions for optimal balance. So basically, the p oscillator is the fast oscillator. So the boundary condition at the time zero end should be just fast oscillations are zero. And then at the fully ramped up end, we want to hit basically a target phase in that case here. So some theta star. And of course, this is basically a scalar linear driven problem. So we can just use integrating factors like in ODEs 101, write out that integral, pull out basically the Fourier series here. And then we do whatever you do in this business, you integrate by parts. And the first integration by parts gives one term here. And and then the remaining integral. And if you look carefully and sort of combine terms, then this first term, including this boundary term from the integration by parts, will simplify to the exact slow manifold. But then there's some garbage, and we have to show that the garbage is actually small because it's not zero. And to show that the garbage is small, you continue to integrate by parts. And okay, I haven't written out all the terms that you're getting, but you can imagine that you're getting higher derivatives of the ramp function that will always be evaluated at the boundary terms. Right? And that basically means that in order for optimal balance to work to high order, the ramp needs to be very flat at the endpoints. Otherwise, at some point, you will get a boundary term. Fortunately, you get sort of positive powers of epsilon in front with every integration by parts. So so whatever boundary terms appear, they are higher and higher order. And if you basically stop this process at some cutoff, let's say you're doing n integration by parts, then you're going, n plus 2 integration by parts will end you up with order epsilon n plus 1. So the important message of this very simple computation is we need necessarily an order condition, namely the ramp doesn't only need to satisfy the condition that it's 0 and 1 at the two ends, but you need, if you want optimal balance to a certain order in epsilon, you need all the derivatives to also vanish at the endpoint up to that order. And that simple computation basically shows you why. Okay, so our example that we are analyzing in a bit more detail is again an ODE system, because with PDEs we have some regularity problems, so it's much more difficult and it's still open. And again, so this sort of looks like a fast equation here, a little bit like in the previous example. So we are looking at a slow manifold where basically given a Q slow variable like the potential vorticity in the GFD case, if we have Q star as the target field, we want to construct an associated P variable here. Right, and then again, we do what I explained already twice. So we have these boundary conditions for the optimal balance problem. So again, if the ramp is turned down, then obviously this is a fast oscillator. So J is just here the canonical symplectic matrix or any skew matrix here. So this is basically oscillating rapidly. So at the linear end, we just need to project out these rapid oscillations by setting the p variables identical to 0. And for the linear problem, that is exact. And again, at the t equals capital T end, we are hitting the target point, and then I wrote the order condition already. Okay, so if you want a picture of that, it's sort of the idea at the little t equals capital T end. We have some manifold m of t, which we believe is the slow manifold. It's not exactly invariant under the flow, but almost invariant. So basically some solution that starts in the unramped, in the original nonlinear problem, that starts on the slow manifold will deviate from it just by little. Now, in this time dimension, I'm showing the ramp, and essentially this nonlinear slow manifold gets slow deformed into a linear subspace, and at the linear end, we have an exact splitting of subspaces. So the fast subspaces in the vertical here, the slow subspaces in the horizontal, and this is just, yeah, at that level is exact. And adiabatic invariance means that if I start a solution here that is initially on the linear slow manifold when the system is linear, that it remains close to the slow manifold as the manifold is slowly being deformed into its final shape. And yeah, it will run away a little bit, but we can show that it doesn't run away much. Right, so this is still a good estimate on the location of essentially these fiber variables over the base point Q star. Okay, so in order to do analysis, and I think this is a slide that I'm going to go over quickly, one can basically do an asymptotic construction just by formal asymptotics and construct basically the slow manifold as an epsilon series. And there are exact expressions in that case, what the coefficients look like. And of course, the number of coefficients grows exponentially through this recursion here. And what is important for the analysis is that we can then introduce a fast variable, which is the original p variable minus the slaved ones through this constructed slow manifold. And then the fast variable is going to satisfy an equation that has 1 over epsilon in front of the skew matrix here, or skew operator. And then there's sort of a linear term and there's a remainder. And the nice thing is when you do energy estimates, well, you hit this equation with W, and then you have a skew term, so 1 over epsilon drops out, and that is basically why everything works. Right? And then the task is to basically estimate the remainder using whatever conditions you have in the problem. And the same construction also works for the ramp system, and then you're picking up a few more terms because the ramp function has explicit time dependence, so there's some, but everything really looks just the same. Okay, so now to do a precise mathematical statement, we need to think about function classes for the ramp function. And I said, well, what we are really targeting is some exponential asymptotics, because we know with the slow manifold business, if we don't have these ramp problems, then we can actually get that solutions remain exponentially close to the slow manifold for exponentially long times in this Hamiltonian perturbation theory. So we want to get exponential results, so we want to do Cauchy estimates or something, but we really can't, because in order to do that, we need to go to arbitrary order, and to arbitrary order, the ramp function needs to be horizontal, and so it cannot be analytic. So to do something, we go to Rivray classes, and one possible ramp function that satisfies the requirements is this one here. So it's basically all its derivatives are 0 at the endpoints. So this is your Ray class 2. And then after a lot of work, we get an exponential estimate, which is slightly weaker than what you would see from the traditional Hamiltonian perturbation theory. Namely, there's an epsilon to the 1/3 here in the exponent. But in any case, so this is the reconstructed slaved variables through the optimal balance. So this is computable, and this is the theoretical optimally truncated series that you get from the perturbation argument. But of course, the number of terms is growing exponentially, so it would be insane or actually impossible to write it out. And we basically say that what we can compute by this very simple method is actually exponentially close to what we would get by the optimal truncation. All right, so optimal balance in primitive variables. So now the question, I'm going a little bit here to a GFD problem. Can we do something in the way most traditional models, if you're not David Ritchell, most traditional models are constructed to sort of increase the base of application for this method? And the natural thing would be to basically put the ramp function in front of the nonlinear interactions. And so this is shallow water here just as one model equation. And then, well, for linearized shallow water, we have the exact modes and we know what they are. So we can do the exact splitting at the linear end. At the fully nonlinear end, we have shallow water dynamics. Right? And so, yeah. So this is probably what I said. So we have a projector onto gravity wave modes, and at the linear end, we simply say that this projection should be 0. And at the nonlinear end, we hit, so in the past, we have hit a target potential vorticity. This can also be done because it's just a kinematic problem at the boundary condition, so that we hit still a target potential vorticity, or we hit a target H field. We find that fixing the potential vorticity is numerically a little bit more stable than fixing the H field, but it's certainly possible also to fix H. Right, but you can construct the remaining variables as a function of H in order to be on the slow manifold. So you're just parameterizing the slow manifold by H. And yeah, so your comment is actually the right one, because you find that in certain parameter ranges, it's a bad parameterization of the slow manifold, and then things go bad. But it works in a surprisingly large range of Rossby numbers. That's all. So just works.
H0? H0 on the right-hand side.
Yeah. Yeah, so that's the deviation. Yeah. Yeah, I guess I. Well, it does, but it's just more corrections. Right? I mean, it becomes numerically unstable for relatively large Rossby numbers, or Rossby numbers that are tending towards 1 from below. And then if you fix the potential vorticity and solve this kinematic problem for the boundary conditions, you can do this very stably, even for Rossby number 1. I mean, whatever you get, I mean, whether it's meaningful or not is another question. And then this one basically simply ceases to seemingly converge. Okay, so we use a nudging solver of the same kind. And this is essentially a careful study done by a PhD graduate a couple of years ago, Tuba Maser. And she actually looked at the nudging iterates in that problem as a function of basically the number of iterations that were done across the spectrum. What she was seeing is, well, it seems to converge very well in the small wave numbers, but as you go up the spectrum, you remain relatively far from sort of a given sort of random target potential vorticity field. So this is the residual after each of the nudging iterations, right? So it doesn't converge too well for the high wave numbers. Right? Maybe not unexpected, but yeah, we see this very clearly here. Okay, and then sort of we started thinking about it, and up to that time, we always thought we should try to aim at well-posedness, to actually show that things converge. And then we went back to the toy problem and actually looked at more closely, really with proofs, what is happening. And so this is the nudging iteration for the toy problem, sort of written out with all the steps again. So this looks very similar, but in slightly different notation, what I had before. So let's say linear end is essentially, again, the p variables are the fast ones linearly exactly, so they need to be discarded and set to 0, where the q variables are simply kept. Okay, forward integration, and yeah, so the forward integration, the p variables, so what we think of should emerge as the slave variables, they are kept, and q is reset to the target q, right? And then we go around in the circle, and we can analyze this in terms of the fast variable. For the proof, it's much better not to formulate this q and p, so q and p is seen by the numerical algorithm, but for the analysis, we want to work with q and the fast variable w. Right? And it turns out by these adiabatic invariance proofs that in these integration steps, the fast variable remains almost constant. I mean, there's exponentially small growth, but it's almost constant. So we should look at what happens to the fast variable in the boundary conditions. So here we are basically setting p to 0, and we should notice that at the linear end, actually p is really the fast variable. So p is w at the linear end, and so the jump that we are introducing here, the discontinuity, if you want, in this cycle, is small if we started with something small. Right? And then here at the end, when we restore the base point, we want to show, and this requires hard estimates, that the jump in Q that we are making in this restoration step is also small if initially we started with a small fast component and went around, came back here. We don't want a big jump in Q. And if we can control that in a more quantitative way, then we have a proof. That's sort of the idea. Okay, so I'll start with the result on quasi-convergence here. So what we can show is that, again, this is the optimally truncated, theoretically available, but not practically accessible slow manifold. This is what the nudging gives us after the nth iteration. And we see that this actually doesn't go to 0, right? So if it were converging, the lim sub or limit of this quantity should actually, this would not be 0, but essentially differences between consecutive iterates should go to 0. Right? And here, so all that we can show is that relative to the optimal truncation, we again remain in an exponentially small neighborhood. that is uniform for all m. So as we go around, we might not stabilize, but we are stabilized in a ball that is as small as the balancing error anyway of the method. Right? But we cannot control any further within that ball. That's the scale separation coefficient, so think Rossby number for the problem that we are really right, yeah, so yeah, okay, so this is the radius of the fuzz here. Okay, so I think I said that. So it's highly effective, but I would call this quasi-convergent, right? So it's convergent for all practical purposes. It does. Well, that's what David already found, right? So they wrote it converges quickly and robustly. Right? So now we should say it quasi-converges quickly and robustly, but it works. I guess that's the point. Right. Yeah, but epsilon can, I mean, you didn't have the exponential ramp either, so it should have been second order, but I mean, for these fluid problems, I mean, that's, I guess, the errors that you would expect anyway, so it will not make a difference. And we also nicely, I mean, at least from the mathematical perspective, in some referees also sort of hit on us during the years also, this well-posedness. So we nicely sidestep the problem because we don't need well-posedness, right? So we just show if we set up this algorithm, it's coming back within a small ball, right? So whether as a boundary value problem, this thing is well-posed, doesn't matter. The proof still works and doesn't require an exact solution to exist. And it may exist or may not exist. We don't know. So we could call this quasi-well-posedness because the residual to a well-posed problem is at most exponentially small again. Not in the sense of the boundary value problem. Of course, we need well-posedness in the sense of the initial value problem that we use to go from one end of this nudging ramp to the other end, right? Of course, if that is not well posed as an initial value problem, we are in deep trouble. Well posed is a boundary value problem in time, where you sort of think of imposing one condition at one end, the other condition at the other end, and having a solution that connects these two conditions is not required. Right? So we are showing we are coming back within a small ball, right? And it might not be well posed in the strict sense, but it's almost well posed because the residual is so small. Okay, and so maybe a nice practical, go back here, practical implication is that sort of this level of non-returning also gives us some quality indication on the balance itself. Because if we basically restarted just a regular forward shallow water simulation with this initial condition, then we would expect essentially rapidly oscillatory wave modes to be excited with sort of, at least initially, the spectral slope. And of course, as these evolve nonlinearly, all bets are off. So we have an implicit control of quality of balance just by looking at how well the nudging iteration returns. Yeah, I guess I'm over time already, or I'm just recovered the time that David took. So I'm not going to talk about the proof. It's in the paper, it just came out last week actually, and SIAM multi-scale modeling and simulation. So let's look at a few sort of things, maybe not everything. So what we are thinking about it right now, let's start from the bottom here. So what do we do with optimal balance with complex models? If we don't have contour advection where things are clear, and we don't have sort of a nice spectral picture that we can explicitly compute at the linear end and have the exact separation into vortical modes and gravity wave modes. Right? So something we found over the years is that this separation can be actually reformulated as an elliptic boundary value problem, not boundary value problem in time, but elliptic problem. But again, that needs to be coded up and is then hard in complex domains if you think ocean basins. But on the other hand, if we have an F-plane model, we know that basically the vortical modes are linear steady state, so we can basically use that in order to detect them with a just an evolutionary forward in time code. So nothing special is required to do that. But if we are not on the F-plane, and this is something we are just beginning to think about, and I would like maybe some feedback from the experts here. Since we have this possibility to put the ramp function basically anywhere we can expect adiabatic transitions, why not deform the dynamics on the sphere into F-plane dynamics, at least as far as the Coriolis parameter goes? So essentially freeze the Rossby waves so that they become exact steady states at the linear end. And as we go to the nonlinear end, to essentially relax the Rossby waves to move as they should move. And then, of course, we could use this basically picking out steady states by averaging the prognostic equations. Right? So, and I guess that would mean that we would need the Coriolis parameter to be constant on each hemisphere and then discontinuous at the equator, or maybe there are other configurations where one can basically freeze the situation in a reasonable way that remains the adiabaticity of the ramp and still gives us non-moving Rossby waves. Right? And then there are a couple of other things you can read. We can discuss further. So thank you.